So in this video, I want to show you about how to use modular arithmetic to solve some number theory problems. And so what I want to do is going to come in two parts. First is I want to show, I won't say prove, but let's show that x squared, if you take any integer squared, that's going to be congruent to 0 mod 4, or x squared is congruent to 1 mod 4 for all integers x. And there's a little shortcut here. I might take both of these modular arithmetic statements and say that x squared is congruent to 0 or 1 mod 4. But I just mean that x will be congruent to either 0 or 0 or 1 mod 4. And so to do this is actually straightforward. When we're working mod 4, we're going to have 4 possible integers that we can work with, 0, 1, 2, or 3, corresponding to the 4 different equivalence classes, because remember that when we're working mod 4, really we're working in the quotient ring of the equivalence relation that we defined before, right, where two integers are related if they're equivalent mod 4. So we can kind of think of working mod 4 as working over the integers where the entire universe of integers is going to consist of just the numbers 0, 1, 2, or 3. And so all we have to do is check that the statement is true for those 4 integers, and then we're done. I'll kind of give you a second way to think about this in a second, but anyway, so the first way, the first method, is we're just going to take x is congruent to 0, 1, 2, or 3 mod 4, square each of these, and then think about what's going to happen to the square mod 4. Now the first two are super straightforward because 0 squared is 0, so that's fine. 1 squared is 1, so that's fine. 2 squared is 4, and 4 squared is 0 because, and 4 is 0 because we're working mod 4s, because 4 and 0 have the same remainder when divided by 4. So when we square 2, we end up with x squared equals, x squared is congruent to 2 squared, which is 4, but 4 is just 0 mod 4. And likewise, when x is 3, we end up with x squared being congruent to 9. 9 is congruent to 1 mod 4. One thing that I want to emphasize here, and this is a little trick in computing these, this is particularly helpful here. If you were to have x is congruent to 3 mod 4, this tells you that x squared is congruent to 9 mod 4. And what you can do is you can keep subtracting 4 until you get a number between 0 and 3. So this works irrespective of this trick, but if you were to take something like 22, you want to know what's 22 mod 4? Well, what you could do is you could take 22 and subtract 18, or subtract 4, you get 18, subtract 4 again, 4 again, 4 again, end up with 6, and then 2. And so the point is that 22 is going to be congruent to all of these numbers, but it'll be congruent to 2 mod 4. So you can always just successively subtract 4 as much as you want. And this is because two integers are congruent mod 4 if they differ by a multiple of 4. So when you subtract or add multiples of 4, you're not changing its equivalency class. So this is the first method. You can just say x has to be 0, 1, 2, or 3 mod 4. Square each of these numbers, check that you get 0 or 1, which is what we got, and we can move on. The second method is you can just do this thinking about if x is even or if x is odd. And again, I'm not going to write out the details. This isn't going to be a great proof, but what I want to do is I want to show you that if x is even, then that number squared will be a multiple of 4. And that's easy to look at because x squared, that's easy to determine because x squared will be 4k squared. That's certainly a multiple of 4 because you can factor 4 out from it. And so that'll be congruent to 0 mod 4. And likewise, if x is odd, that means that x squared is going to be 4k squared plus 4k plus 1. In other words, this will be a multiple of 4 plus 1. So this will be congruent to 1 mod 4. So it turns out that this tells you a little bit more And if we thought about it, this previous method also tells you the same information, that if you take an even number, so those are going to be the multiples of 4 or the multiples of 4 plus 2, when you square an even number, the square will be congruent to 0 mod 4. And when you take an odd number and square it, you'll get 1 mod 4. Okay, and so this is the reason. So this is the first half of what I wanted to show you with modular arithmetic. And you can play this game with, I think it's kind of fun to think about what are all the different squares with different moduli. So if you were to work mod 11, what are the squares that you would get? So this is, I think, is a fun exercise. You and I have different ideas of fun, I understand, but if you were to have x's, say we were to work mod 11, then there would be 11 possible equivalency classes corresponding to 0 through 10. And so it'd be fun to think about what are the different squares that you get when you work mod 10. Okay, so I'll leave that to you. So if you were to square 0, you get 0. Square 1, you get 1. Square 2, you get 4. Square 3, you get 9. If you were to square 4, I'm sorry, we're working mod 11. If you were to square 4, you would end up with 16, which is 5 mod 11. And then I'll let you fill in the rest of these. Okay, so anyways, there's just an aside there. The reason why I wanted to talk about this is that there's actual statements that you can prove now very easily using modular arithmetic, using these ideas. So what I want to do is I want to prove that x squared minus 4y squared equals 23 has no solutions. Okay, and there's I was going to say nothing special about 23. That's not true. This obviously, the statement is false if you replace 23 with others, right? If you had 25, say you could pick x is 5 and y is 0. So you have to pick certain numbers here, and I'll show you what those numbers are. But we want to prove that x squared minus 4y squared equals 23 has no solutions. And the way that we can do that is we'll do a proof by contradiction. So this will be a proof by contradiction. Suppose that there was a solution. So suppose that we had integers, I'll call them x naught and y naught, so that x naught squared plus 4 y naught squared equals 23. And this plus should be a minus, not that it will make any difference. And if these two are equal, if I say that x naught squared minus 4 y naught squared equals 23, then in particular, since these values are equal, they have to be congruent with whatever modulus. So x squared, x naught squared minus 4 y naught squared is congruent to 23, and we're going to work mod 4. The reason why we want to work mod 4 is two reasons. One is that we understand how squares work mod 4. The other is that if we work mod 4, then 4 is just 0. And so this implies that x naught squared is congruent to 23 mod 4, because this 4 here is really a 0 for working mod 4. And if it's a 0, we can just forget about it. Now, what's 23 mod 4? Well, 23 is 20, which is a multiple of 4, plus 3. So that actually means that we would have x naught squared is congruent to 3 mod 4. And that can't happen because, as we just said above, all squares are congruent to 0 or 1 mod 4. So there's nothing that we can do there. So x naught squared equals 3 mod 4 can't happen. This is a contradiction. And this contradicts that x squared has to be congruent to 0 or 1 mod 4. And therefore, if this doesn't work, if we got a contradiction, then there must be no solutions. There must be no integer solutions, x naught, y naught, to this equation. Okay, and so the jargony way that we would say this is we would say that this equation fails mod 4. Okay, so that's exactly how we would say that. So this idea of modular arithmetic is seemingly nowhere in sight when we're talking about how do we determine integer solutions here. But it turned out to be useful anyways. Okay, so this jargony way to say this is that this equation fails mod 4, therefore it has no integer solutions.